हाँ सर।
हाँ सर।
स्क्रीन दिसतंय का?
दिसतंय सर, दिसतंय.
Okay, good afternoon to all of you. We have started a third chapter, a dynamic and functional modeling. From this chapter, we have studied events, states, different operations, and nested state diagrams. Today, we will study concurrency, advanced dynamic modeling concepts, relations of object and dynamic models, then data flow diagrams, then relation of functional to object and dynamic model. So start with concurrency. Concurrency is divided into two parts, aggregation concurrency and concurrency with an object. So we will study first aggregation concurrency. So aggregation concurrency in this a dynamic model describes a set of concurrent objects. A dynamic model describes a set of concurrent objects, each with its own state and state diagram. The objects in a system are inherently concurrent. They can change state independently. So there is no dependency between the objects. So they can change their states from one state to another state independently. The state of the entire system cannot be represented as by single state in a single object. The state of entire system cannot be represented by a single state in a single object. It is a product of all the states of all objects in it. In many systems, the number of objects can change dynamically as well. So a state diagram for assembly is a collection of state diagrams, one for each component. Aggregation implies concurrency. The aggregate state corresponds to the combined states of all the component diagrams. The aggregation is also known as AND relationship. The aggregation is also known as AND relationship. The aggregate state is one state from the first diagram and the state from second diagram and state from each diagram. Aggregation from, suppose there are a number of diagrams, then aggregation is the combination of each states of each diagram, that is known as aggregation or also known as a AND relationship. Suppose your 12th marks, so what is your aggregate? That is the combination of all subjects: English, Marathi, Hindi, physics, chemistry, maths, biology, whatever. That is the combination of all subject is known as aggregation, that is AND relationship. So one subject is related with other subject. So in more interesting cases, the corresponding states interact. Guarded transitions for one object can depend on other object being in a given state. This allows interaction between state diagrams while preserving modularity. So this is the figure. Figure shows the state of the car. Car is an aggregation of different components like ignition, transmission, accelerator, and brake. Here we have taken only four components in case of car. Each component state also has a substates. For ignition also there are many substates. For transmission also many substates. For brake, for accelerator also many substates. So the state of the car includes one substate from each component, and each component undergoes a transition in parallel with all the other. The state diagram, all the components are almost but not quite independent. The car will not start unless transmission is in neutral. This is shown by guard expression. Transmission in neutral, tran- transition from ignition off to ignition starting. So we will see this example in detail. Suppose this is the car aggregation. So it have four components: ignition, transmission, brake, accelerator. We'll see these four components in detail. First component is ignition. So ignition, whenever ignition is off, that is in neutral, then turn key to start, that is transmission in neutral. Whenever turn key to start, it starts and release the key, then ignition is also on. Whenever turn key off, then ignition will stop. Whenever turn key off, then ignition will stop. Initially ignition is off. Whenever turn key start, then transmission in neutral, then ignition is started and release that key. At that time also ignition is also on. Whenever turn key is off, then ignition will off. This is in case of ignition. Then in case of transmission, this is transmission. There are four gears: first, second, and third, and fourth gear is a reverse. So from neutral, so push forward, so go to the first gear, push forward. F for forward, R for reverse, and N for neutral. So push forward, then forward step, go to the first gear, then shift to the upshift to the second gear, then again upshift goes to the third gear. Whenever I want to take the car in a reverse backside, then there should be a downshift from third gear to second gear to first gear, first gear to push neutral, and then you should push the reverse gear. Whenever your work is completed, then stop the reverse gear, go to the neutral, and push forward, then first, then second, then third, and so on. This is in case of transmission. Similarly, we will see in case of brake. So now first we will see accelerator. So accelerator in neutral, it is off. Whenever it depress accelerator, it becomes on. Then whenever release accelerator, it will be off. Then in case of brake, same as accelerator. Initially there is in neutral, that is brake off. Depress the brake, brake is on. Then release the brake, then brake goes to the off position. This is the concurrency of in case of car, that is state, then substate of each object such as ignition, transmission, brake, accelerator. That is a combination of each state of each part or each object. There is known as aggregation. This is the whole diagram for the car ignition, transmission, accelerator, and the brake. Then second part is concurrency with an object. Concurrency within the state of single object arises when the object can be partitioned into subsets of attributes or links, each of which has its own subdiagram. The state of object comprises one state from each subdiagram. The state of object comprises one state from each subdiagram. The subdiagram need need not be independent. That is, it is dependent. Subdiagrams dependent. The same event can cause transition in more than one subdiagram. Concurrency within a single composite state of an object is shown by partitioning the composite state into subdiagrams with dotted lines. The name of overall composite state can be written in a separate region in the box, separated by a solid line from the concurrent subdiagrams. So concurrency with an object, this figure shows the state diagram for play a bridge a rubber. So there are two boys, then pulling the rubber. When a side wins a game, it becomes helpless. The first side to win two games the wins a rubber. In this figure, this is a first part is playing rubber. Either they are playing north south ns, north south, and ew, that is east west. Either they are playing north south directions, then north south wind rubber, or west, then west wind rubber. So there are two types of vulnerability: ns vulnerability and ew vulnerability. There are two parts: not vulnerable and vulnerable. Vulnerable means helpless, so not helpless and helpless. There are two parts. So during the play of rubber, the state of rubber consists of one state from each subdiagram. One state from each subdiagram. When the playing rubber composite, the state is entered. Both subdiagrams are initially in their respective default state, not a vulnerable state. Each subdiagram can independently advance to state vulnerable when its side wins a game. Vulnerable means helpless. So when one side wins second game, the transition occurs to the winner rubber state. This transition terminates both concurrent subdiagrams because they are part of same composite playing rubber, and are they only active when the top level state diagram in that state. So this is a concurrency part. The next part is advanced dynamic modeling concept. In this section, we represent advanced dynamic modeling concepts as well as some refinement on the notations. This section have 5 points. First is entry and exit action. Second is internal action. Third is atomic transition. Fourth is sending events, and fifth synchronization of concurrent activities. So first, entry and exit actions. As alternative showing the actions can be associated with entering and exit state, there is no difference in excessive power between two notations, but frequently all transitions into a state performer the same action, in which case attaching the action to the state more concise. So this is the example. So example is pushing button. Whenever the button is pressed, then it will be opening or motor up. Whenever same button is pressed, then button will be close. So there are two verbs, open and close. So closed, open, opening and closing. So opening and closing, these are the two states. Similarly, closed and open, these also are two states. Opening and closing, these are the running states. Opening and closing, these are the running state, whereas the closed and open, these are static states. So each event the user generates depress event with push button to open whenever initially state is closed. Then whenever user push that button to open and close the door. So each event reverse the direction of the door, but for safety end, a door must open fully before it can be closed. Initially, suppose state is closed. Then whenever button is pressed, motor is up. That is, it is going to opening state from closed state, and it will stop. That is, it is in opening state till it will be fully open. Whenever it will be fully open, then door open, okay, they or motor off. Whenever door is fully open, then motor automatically off. Whenever again press the button, then from open state to door is going to open state to closing state. That is, motor goes to the down. That is the closing state. And when when the door is at complete close, from closing state to closed, so it goes to the this direction. So pressing a depress motor, suppose at that state of closing, again I have pressed a button, then motor up goes to the up side. That is, from closing to it goes to the opening state. From this state, whenever the door is not completely closed, at that time I have pressed a button, then from closing or motor off to closing door or motor off state goes to the opening the door, that is motor on or motor up state. It goes to this direction. See, initially a door is closed. Whenever button is pressed, it goes to the opening state. It will remain in opening state till it complete open. Whenever button is pressed again, it goes to the closing state, and it will close till it will goes to the closing state till it will complete close. But at the state of closing, whenever I have pressed a button, then it goes to the opening state, not to the complete close. It goes to the opening state and the door becomes open. This is entry and exit action. So each event reverse the direction of door, but for safety the door must be open fully before it can be closed. The control generates motor up and motor down action for the motor. The motor generates a door open and door closed events when the motion has been completed. Both transitions entering state opening cause the door to open. Question may be asked for 4 marks. Write a short note on entry and exit actions. So this figure, same figure shows the to entry to the state. An entry action is shown inside the state box. These are the state box. Closed, opening, open, closing, these are the state box. So entry action can be shown inside the state box. And following entry, keyword entry, a slash character is used. Entry oblique motor off, entry oblique motor up, entry oblique motor off, entry oblique motor down. So whenever the state is entered by any incoming transition, the entry action is performed. An entry action is equivalent to attaching the action to every incoming transition. An entry action is equivalent to attaching the action to every incoming transition. If an incoming transition already has an action, its action is performed first. This is in case of entry action. Similarly, there is also exit action. Exit actions are less common than entry action, and exit actions are less common than entry actions, but they are occasionally useful. An exit action is shown inside the state box whenever the state is exited by any outgoing transition. The exit action is performed first. So entry and exit actions are particularly useful in nested state diagrams because they permit a state, possibly an entire subdiagram, to be expressed in terms of matched entry exit actions without regard for what happens before or after the states are active. It is possible to use actions attached to transition as well as entry and exit actions in a diagram. Transitioning into or out of a substate in a nested diagram can cause execution of several entry and exit actions. If the transition reaches across several levels of generalization, the entry action are executed from the outside and the exit action from the inside to outside. Entry action executed from outside to inside, whereas exit action performs from inside to outside. This permits behavior similar to nested subroutine calls. Then second part is internal actions. An event can cause an action to be performed without causing a state change. We know that the Newton's third law, every action there is equal and opposite a reaction. Similarly, an event can cause an action when without causing a state change. Whenever an object is a state change a state from one state to another state, at that time event can cause an action. So event name is written in a state box followed by slash and the name of action. See in this figure, Here state first. Then do activity first. What is the activity first? Entry. Activity first is entry, then slash action 2. Action 2. Then exit slash action 3. Then event slash action 4. So the keywords entry, exit, do are reserved keywords within the state box. When such an event occurs, its action is executed, but not the entry or exit actions for the state. There is therefore difference between an internal action and a self transition. The self transition causes the exit and entry action for the state to be executed. So this figure summarizes additional notation for entry, exit and internal action. So whenever event first, that is attribute first, then this attribute have the coordinates, that is action first. So suppose this is event second, then it have attribute second. So this is regarding to object class. Event first is regarding to the state. So then third is atomic transition. Automatic transition. Frequently the only purpose of state is to perform a sequential activity. When the activity is completed with the source state fires. Frequently, the only purpose of state is to perform an sequential activity. When the activity is completed with the source state fires, the arrow without an event name the arrow without an event name indicates an automatic transition that fires when the activities associated with source is completed. If there is no activity, the labeled transition fires as soon as state is entered. But the entry and exit actions are always performed. If a state has one or more automatic transitions, if a state has one or more automatic transitions, but none of the guard conditions are satisfied, then the state remains active until one of the condition is satisfied. If the state has one or more automatic transitions, but guard conditions are satisfied when the one of them condition is satisfied or until an event cause another transition to fire. So change in the condition is implicit event. Change in condition is internal. For example, temperature below freezing is a condition. So temperature goes below freezing is age triggered event associated with that condition. Some material, suppose some material requires temperature below freezing. This is the condition. But the event associated with that condition is temperature goes below freezing. This is the event, and the condition is temperature is below freezing. Then next concept is ascending event. An object can perform an action. An object can perform the action of sending an event to another object. The system of object interact by changing event. The action send E. E means event. The action send E So sends event E with the given attributes to objects that receive it. This is the action. So for example, in case of phone line, the phone line sends connect phone number, that is phone number, the event to switcher when complete phone number has been dialed. An event can be directed at a set of object or a single object. Any and all object with transitions on the event can accept it concurrently. The word send can be omitted if it is clear that is name of event. In our diagram, event names are shown in italic and one digit. Action name italic and digit 1. Action names in normal text so that there is no confusion. Then next part is a synchronization of concurrent activities. Sometimes one object must perform two or more activities concurrently. Sometimes one object must perform two or more activities concurrently. The internal steps of activities. The internal steps of activities are not synchronized, but both activities must be completed before the object can progress to its next state. For example, consider a cash dispensing machine that dispenses cash and returns the user's card at the end of transaction. This is example of ATM. So the machine must not reset itself until the user takes both cash and card, but the user may take them in either order or even simultaneously. The order in which they are taken is irrelevant. Suppose here given sequence is first take the cash and then take the card. But sometimes we take first card and then we take cash. Here the order is irrelevant. So only fact that both of them have been taken or not. If both of them have been taken, then machine update itself. This is an example for splitting control into concurrent activities and later merging that control. So this is the figure of nearly about this is figure of ATM. So this figure for emitting activity, concurrent activities with a single composite activities. Suppose I want to take some money from ATM by using my ATM card. So go to the setup, enter my password, enter my card, then enter my password, and I want to withdraw. I want to withdraw some money. So press a withdrawal button and enter a specific amount. Then emitting do dispense cash, and this is the first activity, as well as the second activity is eject that card. So cash taken and card taken both are done by simultaneously, or first I have taken cash and then second I have taken card, or third possibility is first I have taken card and second I have taken cash, but whenever both cash and card have been taken, then machine is ready to reset itself. So is each region is a sub diagram that represent a concurrent activity with composite activity. The composite activity assumes exactly one state from each subdiagram. This is the synchronization of concurrent activities. A sample a dynamic model. So we represent a sample dynamic model of a real device to show how various modeling constructs fit together. This model is Vikander programmable. Okay, this is the big example. So mm, this is a big same sample diagram big example. Then next part is a relation of object and dynamic models. The dynamic model specifies allowable sequence of changes to objects from the object model. A state diagram describes all or part of the behavior of one object to a given class. States are equivalence classes of attributes and link values for the object. Event can be represented as operations on the object model. So relation of object and dynamic model. So in this the dynamic model structure is related to and constrained by object model structure. The substate refines attributes, links, and values that the object can have, but the refinement of object values exactly generalized by restriction. The hierarchy of states of an object is equivalent to the restriction of hierarchy of object class. Object-oriented models and languages do not usually support restriction in the generalization hierarchy. So the dynamic model is a proper place to represent it. Both generalization of class and generalization of state partitions the set of possible object values. A single object can have different states over time. The object preserves its identity, but it cannot have different classes. Inherent differences among objects are therefore properly modeled as different classes, while temporary differences are properly modeled as a different states to the same class. So a composite state is an aggregation of more than one concurrent substate. There are three sources of concurrent within the object model. The first is aggregation of object. Second, the source of aggregation within an object. And third is the behavior of an object. So first is aggregation of an object. Each component of an aggregation has its own independent state. Each component of an aggregation has its own independent state. So the assembly can be considered to have a state that is the composite of the states of all its parts. The second source is aggregation within the object. The attributes and links of an object are its parts, and groups of them taken together define the substates of the composite object state. And the third is the concurrent behavior of an object. The three sources of concurrency are usually interchangeable. For example, an object could contain an attribute to indicate that it was performing a certain activity. So dynamic, this is in previous slide we have seen regarding the object model. In this slide we will see relation regarding the dynamic model. So the dynamic model of a class is inherited by its subclasses. The subclasses inherits both the states of the ancestor, that is the previous, and the transitions. The subclasses can have their own state diagrams, but how do the state diagrams of superclass and the subclass interact? We have noted that states are equivalent to restriction on classes. If the superclass state diagrams and subclass state diagrams deals with a disjoint set of attributes, then there is no problem. The subclass have composite state composed of concurrent state diagrams. If, however, the state diagram of subclass involves some of the same attribute as a state diagram of the superclass, a potential conflicts exists. The state diagram of superclass must be refinement of state diagram of superclass. Any state from the parent state diagram can be generalized or split into concurrent parts, but new states or transitions cannot be introduced into the parent diagram directly, because the parent diagram must be a projection of a child diagram. Although refinement of interact although the refinement of inherited state diagrams is possible, usually the state diagram of subclass should be an independent orthogonal concurrent addition to the state diagram inherited from the superclass, defined in different set of attributes, usually the ones added in the subclass. So the event hierarchy is independent of the class hierarchy. The event hierarchy is independent of class hierarchy in practice, if not in theory. Event can be defined across different classes of objects. Events are more fundamental than the states and more parallel to the classes. Events are parallel to the classes and it's are basic than the states of that classes. States are defined by interaction of objects and events. States is the combination or interaction of object and events. Transition can often be implemented as operation of objects. The operation name corresponding to the event name. So events are more expressive than operations. However, because the effect of event depends not only the class of object, but also it depend on its state also. Then next part is a data flow diagram. In previous lecture we have seen, but we will study once again. The data flow diagram is an object methodology technique diagram that is added to the UML, that is Unified Modeling Language suite, when you activate your OMT module. Purpose of a DFD is, in OMT you use DFDs to model what happens with data. You model the system as a network of processes that transform and exchange data. The DFDs also shows the flow of data values from their sources in objects through the process that transform them to their destination in object other objects. Values that can include input values, output values, and internal data stores. Control information is shown only in the form of control flows. So there are four parts in the DFD. First, processes. Second, data flows. Third, actors. And fourth, data stores. And other two parts of DFDs are constraints and control flows. We'll see the detail in. So first is processes, features of processes. The processes are computational activities that transform data values. A process may be further divided into smaller components. The lowest level process may be simple function. For example, suppose I want to calculate the HCF and LCM of two numbers. So for this calculation, I require some input so that I can generate some output. So for input, so for operation of LCM and HCF, there is input minimum two integers, integer A and integer B. Then I can calculate a required LCF and LCM. So these inputs in integer A and integer B, these are the inputs. Then this is the process, that is calculation of HCF and LCM of A and B. And this is required LCM, this is required HCF. These are the outputs regarding that process. Second is a data flow. Data flow represents the flow of data between two processes. It could be an actor and a process, or between a data store and a process. There are data flow from two processes. First, either actor and process, or between data store and process. But in these two states, process is also common. A data flow denotes the value of a data item in some point of the computation. The data value is not the data value is not changed by the data value. So there are two figures. So suppose I want to calculate, in first figure I want to calculate sum of some numbers. So suppose I have taken the three numbers and I want to calculate sum of these three numbers. So this sum is aggregation of these numbers. These numbers, suppose A, number B, number C. So number A, number B, number C is a part of this sum. Similarly, in second figure, name is aggregation of your first name, middle name and last name. So your first name, middle name, last name are the parts of a full name. So then next part is actor. Actors are the active objects that interact with the system by either producing data and inputting them to the system, or consuming data produced by the system. In other words, actor serves as sources and sinks of data. So here in this figure, there are three types of actors. First is customer. Second, sales. This is the process. There are two actors. First is customer and second is clerk. So whenever customer gives the details or ask for details, then this is the process, so that the clerk will check the sales details and give the information of regarding sales to that customer. So then next part is the data storage. stores. Data stores are the passive objects that act as a repository of data. Unlike actors, they cannot perform any operation. They are used to store data and retrieve the stored data. They represent a data structure, a disk file, or table in database. Then constraints. Constraints specify the conditions or restrictions that need to be satisfied over the time. They allow adding new rules or modifying existing ones. Suppose there are two departments, HR department and sale departments. So both require employee. So employee is a common factor. Employee details also common factor. So it may be from either sales department or either HR departments. Then next, control flows. A process may be associated with certain boolean value is evaluated only if the value is true, though it is not a direct input to the process. These boolean values are called as control flows. So suppose in case of division operation, there is input divisor and dividend. These are the inputs and required outputs are quotient and a remainder. But before the operation, we must confirm that whether the divisor is not equal to 0. If it is true, then go to the division so that we can find the required quotient and remainder of given divisor and dividend. The last part of this chapter, a relation of functional to object and dynamic models. The functional model shows that what has to be done by a system. What has to be done by a system. The leaf processes are operations on objects. The object model shows the achievers, the objects. Each process is implemented by a method on some object. The dynamic model shows the sequence in which operations are performed. Each sequence is implemented by sequence, loop, or alternation of statements with some method. The three models come together in the implementation of methods. The functional model is guide to the methods. So relative to functional model, the object model shows a structure of actors, data stores, and flows. In the functional model, the dynamic model shows the sequence which processes are performed. Relative to object model, the functional model shows the operations on classes and the arguments of each operation. It is therefore shows the supplier client relationship among classes. The dynamic model shows the states of each object and the operations that are performed as it receives event and changes a state. And last, a relative to dynamic model, the functional model. Relative to dynamic model, the functional model shows the definition of leap actions and activities that are undefined with a dynamic model. The object model shows what changes, states, and undergoes the operation. So we have completed a chapter third.